Okay. So good evening, everybody. I'm going to be presenting, making a video. I'm making a video on recurrence, recurrence relation. Or sometimes you can call it recursive relation. Recursive relation. So if you have done a programming class, especially maybe C++ or Python, you might probably have heard about what is called recursion. Recursion, when a function calls itself, right? When a function calls itself, that situation is called a recursion. For instance, if I define a function 1, right, which is in C++, for instance, integer function in C++, which is actually returning a sum of two integer parameters. So in the body of the function, I could say return function 1, x minus 1, y minus 1. Now, this is possible. This is a recursion. You can see that this function 1 is defined in terms of itself. Okay, that is called a recursion in computer programming. And when it comes to relation, you also have what is called recurrence relation. For instance, if you look at this, right? This is n. Suppose that's n. To the right of n, you can have n plus 1. And to the left of n, you can have n minus 1. Okay? And you can use these values as a subscript for expression. For instance, you can define Tn in terms of Tn minus 1 plus Tn minus 2. You see, I can define this one here, Tn plus 1, in terms of Tn plus Tn minus 1. Something like this is called recurrence relation. Recurrence, that is C. Relation, recurrence relation. And there are a lot of them. I have some examples I've written down here. There are lots of them. Example 1 that we would like to consider, it's given that an equals n minus 1 plus n, with a naught equals 4. right? Show that generally an is giving us 4 plus n into n plus 1 divided by 2. Look at that. Show that now this is obviously a recurrence relation. Do I have any space? Okay, I've written it here. Okay, let me see if I can move this down. Why is it not? It's frozen. Okay. Let me grab this. Let me grab this. Sorry about that. So let me grab that and put that here. Okay, yeah, look at this question. Now, this is a typical question on recurrence relation. Use iteration to solve recurrence relation. An equals an subscript 1. Now, this n here, they are just subscripts. Like if you have list of terms, T1, T2, T3, T4, Tn. These numbers are just positional index or subscripts. Subscripts. Right? Okay, so this is a T1 coming first term, T2 coming second term, T3 coming third term, and I can define T3 in terms of T1 plus T2. That is possible, right? That means I can define Tn plus 1 in terms of Tn, previous one, plus Tn minus 1, right? If your n is 2, if your n is 2, you have T3 here. See that? Equals T1 plus T2. So all these are just notation, okay? They are just notation. Let me. I need to delete that. Okay. Okay, now to solve, we've discussed in this class, we've discussed arithmetic progression and geometric progression, right? Arithmetic series, AS, and geometric series. And I've told you what those mean. They are common elementary ones that you even come across in middle school, you know, I mean, high school, okay? But there is a generic, there is further techniques that captures non-geometric and non-arithmetic recursive relation. And we normally use, most popularly, we use two methods of solving. Two methods of solving recurrence relation. Number one, you have iteration method. Iteration method. Number two, you have method of characteristic equation. Method, now two methods that are most popular, iteration method and methods of characteristic equation. Okay, now I'm going to show you how to use those methods. Now we have the question here, use iteration method to solve the recurrence relation, right? An given as an plus minus 1 plus n. Given that initial condition, you can call this initial condition. Initial condition, A naught equals 4. Show that this is the solution of the recurrence relation. In other words, this formula is what you can use to get any terms of this sequence or of this relation. That is the solution, that is the formula. So with this formula, you can predict the next time. So let's see how we can use that. Now, solution. You have an equals an minus 1 plus n. Look at that. Remember, n minus 1, n are just subscripts. So that means a1 will be given as what? A0, because 1 minus 1, if your n is 1 here, see, 1 minus 1 will give 0 here, okay? So, let me clean that up. Oh boy. So equals an. So I have an equals an minus 1 plus n. So that means your a1 will be given as a naught, which is a0. Choose n to be 1. Plug 1 here, plug 1 here. That will give you a1 equals to. Remember, your n is 1, so plus 1. Now you have to leave it that way. Don't plug in this number 4 yet, okay? Do not plug in this number 4 yet. Just leave it as a naught plus 1 on the right side. Similarly, if you define your a2, you're going to have a1. Now your a2, that is when your n is 2. So a2 equals a1 plus n. So n is 2. You see that? And your a1 is already given as this one. So your a2 just becomes a1. Your a1 is this, plus 2. Because this is my a1, see? a1. So that means I can define my a2 in terms of the a naught. A naught is the original initial value. So my a2 can be defined as a naught plus 1 plus 2. Similarly, I can define my a3 as using this formula. Using this formula, always remember this. I can define my a3 in terms of a2. See that? Just next one equals previous one plus n. So a3 is going to be a2 plus 3, because we are looking at n to be 3. That's the third iteration. Third iteration. Third what? Third iteration. Okay, so now we can replace our this with our a2. See, so your a3 now becomes a3 equals, instead of writing this, I'm going to write this, a naught plus 1 plus 2. This is my a2, then plus 3 here. So that becomes a3 equals a naught plus 1 plus 2 plus 3. Now, you are going to be defining all subsequent terms in terms of your a naught. I suggest do not plug in the value of a naught while you are doing the iteration. It will lead to confusion. So you can see when I have 3 here, a3, I have 3 here. When I had 2 here, I had 2 here. So we continue this way, an is going to be a naught plus 1 plus 2 plus 3 plus n. It's going to be the last one. And I've given you a formula before that the sum of the first n natural numbers is given as n into n plus 1 over 2. And we know that our A naught is 4. So A naught is what? 4 plus n into n plus 1 over 2. And that proves that is the solution to that recurrence relation. Look at that. Is that not beautiful? Okay, let me see if I can do more method. I'm not sure if time will permit me to solve more. That is for method of iteration. Okay, then the second method of characteristic equation. Method of characteristic equation. Okay, I think method of characteristic equation. Suppose, I wrote it down somewhere. Suppose we have I think I have it down as a notes. Let me see if I can remember. Yeah, okay, it's here. Suppose we have this relation, right? And we want to solve it by method of characteristic equation or roots. All we have to do, it's so we will write out the expression an equals an minus 1 plus 6 an minus 2. Now I told you these are just notation for the position, right? If you arrange items, so this is, if this is an n, before n you have n minus 1, and before n minus 1 you have n minus 2 as a positional index. So I can now say an, the next term, equals sum of two previous terms. So this is it. So that means I can say Tn equals Tn minus 1 plus Tn minus 2. Okay, but for this particular example, you have to assume, now take note, you have to assume you can represent this as a polynomial, r raised to the power n, because of this n, plus we've got r raised to the power n minus 1. Okay, now, or better still, you can rewrite this as an minus 1 minus 6 an minus 2 equals to 0. You see that? Characteristic equation. Now, you can assume a polynomial of this form for your an. Just write r raised to the power n minus r raised to the power n minus 1 because of this subscript. The minus, now we have 6 here, 6 r raised to the power n minus 2 equals to 0. And you can factorize and bring your r n minus 2 out and get r squared minus r minus 6 equals 0. This one goes here to become 0. So I will finally have r squared minus r minus 6 equals 0. And I can solve this by factorization. I think I can use r squared minus 3r plus 2r minus 6 equals 0. I can bring r out, r minus 3 plus 2 into r minus 3 equals 0. So r plus 2, r minus 3 equals 0. That gives me r equals to -2 or 3. And I think that is what the textbook got. Yeah, -2 or 3. So r is called -2 or 3. So now, when you have something like this, right? Naturally, if you just have it as an equals to an minus 1 plus 6 an minus 2. You can just bring everything to the left side and have an minus 1 minus an minus 2 equals 0. Now, and you will, the first term, just write it as r squared minus r, then minus 6. The power will be reducing. You will start, you know, I've been able to factorize it from here, bringing out this. So I'm left with this. So when you have that, bring everything to the left side and start making up your characteristic equation with r squared for the first term, minus r for the second one. And because of this, of course, this will not have or r raised to the power 0. Okay, so because of this 6, so you have to put minus 6 here, equal to 0. And then you will solve that. Okay, now, if so, the formula says, given the relation an plus alpha an minus 1. Alpha is just a coefficient of this, of the terms, plus b into, beta into equals 0. This will give you the following characteristic equation: r squared plus alpha r plus beta equals 0. We just need to have the first one to be r squared. The second one has got alpha here, so I'm going to keep that alpha. Of course, it's going to have r. Notice n minus 1. So if the power of this one is 2, you must start with 2 for that. The power of the next one, which is n minus 1, we want r1. So then you will solve this. Now, if we get two different roots from, let me call it equation 1, from 1, we use the solution. We use the solution an equals a first root raised to power n plus coefficient b. A and b are just arbitrary coefficients. Remember, you will get your r1 and r2 when you solve this quadratic equation, for instance. But this is a general one. This is a generic one. So when you solve quadratic function, you are going to have two solutions, r1 and r2, because the highest power of quadratic function is what? 2. So, and it's a polynomial of degree 2. You must have two solutions. So we have r1 and r2. So if the solutions are distinct, if the roots are distinct, then the solution to this recurrence relation will be this. An equals, let me use this a, let me use uppercase a plus b r to n. Now you you will use this only when you have two different roots for the initial solution. So let's see an example. This is very, very, very important. Okay. Now, when we see a particular example, it will become very clearer. Okay. So let's say example 1, solve the recurrence relation an equals 7an minus 1, 7an minus 1 minus 10an minus 10, sorry, 10an minus 2 with a0 or a0 equals 2 and a1 equals 3. Those your a0 and a1 are just the initial condition. Okay, that is the technique. It's not like so. Now to solve this, now this is what you had originally: 7an minus 1 minus 10an minus 2. To solve this, bring all the right side to the left side. You have to rearrange them, and then you have 0 at the right side. So you're going to have an minus 7an minus 1 plus 10an minus 2 equals to 0. You see that? Now I told you, now we are very lucky here. The subscripts are in as descending order. So if you start your an with r squared polynomial, we've got minus 7 here, minus 7r. So the power of this one will be what? You can say 1 if you like, but you don't have to put 1 there. So minus 7r plus, there's a 10 here. So 10. You can put 10 raised power 0 if you like, or you know. Now instead of see how the power is decreasing, r squared 2 1 0 and equals to 0. So you can rewrite this as what? R squared minus 7r properly plus 10. R raised power 0 is 1 equals to 0. And when you solve this expression, you're going to have r in bracket 2 into r minus 5 equals to 0. So your r equals to 2 or 5. Look at that. R equals to 2 or 5. Now, these are what? These are two distinct roots. And when you have two distinct roots, you're going to make use of this formula, which says for the solution A equals A root 1 raised to power n plus B root 2 raised to power n. Okay, now this is the representation, but we are not done yet. We need to determine the value of alphabet uppercase A and B. We know that A0, our A0 is 2, right? And our A1 is 3. So you come right here, you will write, now A0 means n equals to 0. And A1 means n equals to 1, right? So I'm not going to write A0 equals A R1. Now my R1 is 2, oh, and my R2 is 5. 2 roots. One root is 2, the other root is, you can call this R1, you can call this R2. So I'm going to have A2 because of this R1 raised to power 0 my n is 0 for this value. So 1 equals a naught. My a naught is, no, my a naught is 2, sorry. So my a naught is 2. My a1 is 3. So equals a r1n plus b, r2 is 5 raised to power 0. Okay, so I can remove this. I don't need that. I'll just say 2 equals anything to the power 0 is 1. So this becomes a plus b. I'm going to call that equation 1. Equation 1. Again, similarly, a1 equals 3 means that your n is 1. Okay, so 3 is our a1. And when you have your a1, you want to use this formula all the time. See, this formula all the time. That's a, and r1 is 2 raised to power 1. We did 0 here, plus b 5 raised to power 1. See, my what is it? Yeah, this is what's happening. Yeah, so this is my R2, and this is my R1. See, R2, R1. Okay, so we have that. And this is just a notation. I can remove this and write 3 equals to 2a plus 5b, equation 2. And now, at this class, I'm not going to tell you how you can solve these two simultaneously. If you solve this, you can combine these two equations and write a plus b equals a plus b equals 2, equation 1, and then 2a plus 5b equals 3, equation 2. So you are going to solve those two equations simultaneously, and that will give you a to be what? 7/3, and b to be -1/3. Okay, so therefore, remember, but our solution is an equals a r1n plus b r2n. I know my r1 to be 2 and r2 to be 5. So I'm going to have general solution as what? A equals what? 7/3 times 2 raised to power n plus, is it -1/3? I want to be sure. Yeah, -1/3. So -1/3. So -1/3, because this is negative here. So bracket R2 is 5 raised to power n. So this is the generic solution for, if you want to predict, we can use this for prediction, right? We can find A10, we can find A17, we can find A18, because all we have to do, for instance, say find now we can predict. Now we can get any values of the terms, because we have the solution. Say, let's say, what is A4? A4 is when n equals to 4. I'm going to come right here. I'll say A4 equals 7/3 into 2 raised to power 4 minus 1/3 into 5 raised to power 4. Yeah, you can just leave. You can leave it like that. You can leave it like that. So, and you can compute it. You can multiply. You can multiply your A4 equals 16 times 7/3 minus whatever you get here This is 625 over 3. You get something. So that's your, it will give you a number. A4 will give you a number. So this is not a geometric sequence, and it is neither a geometric sequence nor a what? An arithmetic progression. So that is the standard formula. So in essence, we have been able to derive a function that we can use for prediction, because in mathematical modeling, in mathematics, the essence of function is to be able to predict. You want to get the next times. You want to forecast. Okay. So let's see another. Now, the one I've just done for you is two different roots. Let's see the case of repeated roots in characteristic equation. Repeated roots. So suppose the recurrence relation an alpha an minus 1, the alpha just means any number, like, you know, in this term now, the alpha here, see, the alpha here is what? 7. Beta is -10, can be anything. So suppose an equals alpha an minus 1 plus beta an minus 2. Okay. Suppose this, let me write it properly. This look awkward. Suppose the relation an equals alpha an minus 1 plus beta an minus 2 as a characteristics equation with repeated roots, just one root. That is what it means. If you have done quadratic function before, repeated means what? Two equal roots, same roots. Normally, when you solve quadratic expression, you must have two solutions. You can get the same solution 2 times. That is what is called repeated roots. Okay, you are going to use the formula an equals arn plus bn rn. Look at the differences between them. This has got extra n. This one here does not have n beside it. See, no n here, no n here. So this has got what? N, right? N beside it. Okay. So let's see an example. Example 2. Solve the relation. Now, I'm going to be skipping the word recurrence because we know that we are talking about recurrence. Solve the relation an equals 6an minus 1 minus an minus 2 with initial conditions. A0 equals 1 and a1 equals 4. A1 equals 4. Okay, so now that is the question. Now the case we are considering now is characteristic equation with repeated roots. Oh, my battery is going down. I need to charge my laptop. So hang on 1 moment. I need to charge my laptop. Okay. Okay, cool. Now, we are considering what? Now, solution. Write out the original expression first. Okay, write out first, then move the right side to the left side. So you have an minus 6an minus 1 plus 9an minus 2 equals 0. Then you write out the next. So that's step number 1. Step number 2, write the characteristic equation. Remember the leading, this is a leading one. See, n is the leading one, n minus 1, n minus 2. So you are looking at n in terms of position. See, if you have n here, you have n minus 1 here, you have n minus 2 here. So this is a leading guy. So the leading guy, so you write its characteristic equation as r squared. You can use any variable. I may decide to use x, but let me just use r squared minus, because I've got 6 there. See, 6. See, you're talking about alpha, the coefficient. That's our 6 now. So r squared minus 6. Now you can write 1 there. The power will be decreasing. Then plus 9r0. Okay, but I can rewrite this as what? You can rewrite this as r squared minus 6r plus 9, because anything to power 0 is 1. And if you solve this by quadratic, we are going to have r minus 3 bracket r minus 3 equals 0, and that will give you r equals 3 twice. Okay, so we have the same root, and the formula says when you have, we are looking, remember, we are looking for solution to this expression, which we can then use or be using to make prediction to get subsequent terms. Okay, and when you have equal roots, the techniques tells us that you are going to make use of this solution, an equals, so the solution is an equals uppercase. Now, I am not going to use R1 and R2 because we have the same solution. I'll just use R and R. So ARN plus BNRN. Okay. And luckily we have our A naught, but A naught equals to 1. That means that is when your N equals to 0. And also your A1 equals to 3. That is when your N equals to 1. Okay. So we have A naught equals to 1 equals to A R raised to power 0. Remember, N is 0 plus B times 0. You have 0 here, R raised to power 0. Now I have my R as 3. My R as 3. So I can put 3 here, 3 here. Okay, so anything to power 0 is 1. So I can remove this part and just say 1 equals A. This becomes 0. So my A equals 1. Okay, that is equation 1. Again, A1 equals 3. See that? According to the question, is it A1 equals 4? Yeah, sorry, A1 equals 4. A1 equals 4. Okay, so I'm going to write A1 equals 4. And when A1 equals 4, that is when your N equals to 1. See, A1, AN. So my N is 1. So I'm going to have A into 3 raised to power 1. Remember the formula, R raised to power N. Okay, plus B times N. My N is 1 times 3 raised to power 1 again. So I don't need this again. So I need 4 equals 3a plus 3b. That is equation 2. So I'm going to solve a equals to 1, equation 1, then 3a plus 3b equals to 4, equation 2. If you solve that simultaneously, you are going to have a to be, of course, a is already 1. So a is 1, and b is going to, if you plug in the value of a here, so you have 3 into 1 plus 3b equals to 4. So I've got 3b equals to 4 minus 3. That will give me b equals to 1 over 3. So a equals to 1, b equals to 1 over 3. So I can now have an, but my an is what? ARN plus BNRN. See the n in the middle? So my AN solution is what? 1 times 3 raised to power n plus 1 over 3, that's my B, times n times 3 raised to power n. My R is the same. So I'm going to have AN as 3 to the n plus n over 3 bracket 3 to the n. And if you like, you can bring out your 3n, 1 plus n over 3. So that is the solution of that recurrence equation. Okay, that is the solution of that. And I think that should be enough. See, let me see if I will solve more questions on the recurrence on Monday. Okay, finally, let's do more question. One more question on principle of mathematical induction. Okay, let me see. I'm not so satisfied with the question I solved for you guys in class. So I want to give you more example. So principle of mathematical induction, PMI, principle of mathematical induction, PMI. So let's have this question, right? Proof that for all n, now you know what this means, for all n in natural numbers, that 6 raised to power n minus 1 is a multiple of 5. Or you can say, you can rewrite this as for all n, for all natural number n, 5 divides 6 raised to power n minus 1. 5 divides 6 to the power n minus 1 is the same thing. Now, you remember the method I told you? So solution, you will represent P of n like a statement. Let P of n equals what? 6 raised to power n minus 1. See that? You have to be careful. The minus 1 is not on top there. No, the minus 1 is separate. Okay, so step number 1. So basis step. Choose n equals 0 and find P of 0. So P of 0 is going to be 6 raised to the power 0 minus 1 equals 0. And we know, this is very true, this is very trivial. 0 will divide any number. So 0 divides that. Okay? 0 divides that. And of course, we know that 0 divides 5 because we want to, we got 5 divide 0. I have to do it the other way around. And we know that 5 divides 0. That is, you can write 0/5. So I'm using 5 to divide 0. So you can divide 0 by any number. You can have 0/4. So that is very, very trivial in mathematics. So this is great. Then step number 2, we call it inductive hypothesis. Inductive hypothesis. So how do you do that? You choose n to be k and look for p of k. So if n is k, now remember we have p of n. You have to start with a variable, then choose another variable, p of n. So p of k is going to be obviously 6 raised to power k minus 1. So now this is very, very important. It's an hypothesis. You have to assume that for this, for every k, for every natural number k, you have to assume that 5 divides 6 raised to power k minus 1. That is not negotiable. Some people call it cheating, but so that is step number 2. Then step number 3. Step number 3. Choose, you have to move ahead. And that step number 3 is actually called inductive steps or inductive improvement. So choose n instead of k, choose n to be what? K plus 1. So therefore, we are going to look for p of k plus 1 to be what? 6 raised to the power k plus 1. See, whatever you have here must be here. See, then minus 1. So p of k plus 1 is written as 6 raised to the power k plus 1 minus 1. Now, the next thing that we have to do here is we have to prove. Now, this is the most important and the most difficult part of PMI. Now, we need to show that 5 will divide 6 raised to the power k plus 1 minus 1. Like 5 divides that. It means that 5 will divide that expression with remainder 0. Okay, so and that means I have to write 5 can divide 10, 5 can divide 15, 5 can divide itself, 5 can divide 20, 5 multiples of 5. So I have to assume that this expression, so next we write this expression 6k plus 1 minus 1 as a what? Multiple of 5 for every m in what? In this, yeah. So we have to assume the right side. That circle is a multiple of 5. And that means 6 raised to the power k plus 1 equals 5m plus 1. 5m plus 1. So, and indeed, 6 raised to the power k plus 1 can be written as 6 raised to the power k times 6 raised to the power 1 equals 5m plus 1. Okay? So, if I divide, I can make this as, what did I do? Okay, so from here, after assuming that 6k, this circle here is a multiple of 5. I can actually write this as 6 raised power k plus 1 minus 1, equals 5m plus 1. Okay, 5m plus 1. So, sorry. So we need to show, that I'm messing up things. So, this has been an hour video. We need to show that 5 divides that. But we know, sorry about that, we know already, according to inductive hypothesis, that our 5 we always divide 6 raised to the power k minus 1. So, but we know that 5 divides 6 raised to the power k minus 1. That means we can write 6 raised to the power k minus 1 as a multiple of 5. And that will make my 6 raised to the power k to be 5m plus 1. Okay, 5m plus 1. Now, this is a valid expression based on our assumption. We can now, to get 6 raised to the power k plus 1, we have to do 6 raised to the power k plus 1 is actually 6 raised to the power k times 6 raised to the power 1. And we know that 6 raised to the power k is already 5m plus 1. So I'm going to replace this with what? 5m plus 1 times 6 raised to the power 1. And that will give me 30m plus 6. Okay, 30m plus 6. So 30m plus 6. But you know that 6 raised to the power k plus 1 minus 1, it's required. I'm just expressing this as this, but we need to show that 5 divides this. So we will now write expression for this rectangle, which is actually 30m plus 6 minus 1, and we will have 30m plus 5. And then we can factorize and bring 5 out. 5 into 6m plus 1. Now, this is a multiple of 5. I have been able to express 6 raised to the power k plus 1 minus 1 as a multiple of 5. See, therefore, my 5, we always divide any expression of this form, given that k is a natural number. So that is the end of my video. See, I've covered many concepts, and I hope this is very informative for you. Just pause, check my video. If something is not clear too much, consult the course textbooks, and you'll be fine. I will see you next time. Thank you.